Hello and welcome to our next lecture in CHY 113. So far in this unit, we've been looking a lot at chemical reactions. We started by looking at some of the basics of reactions, looking at how we represent reactions in chemical equations, the balancing of equations, and so forth. From there, we moved on to the amounts involved in chemical reactions and how we figure out how much product, for instance, might be created if we have so much of our given reactants, and so forth, looking at basically everything having to do with the amounts of things in reactions. Today starts our last phase of the study of chemical reactions and looking at the energy involved in reactions. It turns out that all matter changes, doesn't matter what type of matter change it is, chemical or physical, all changes in matter have some sort of accompanying energy change or energy difference. And so that's really what makes up what we'll be studying in these last few lectures, is looking at those energy changes. We'll look at some involved with some physical changes, some states of matter, and we'll look at some energy changes that are associated with chemical reactions and various chemical processes. And so when we take a look at just sort of our objectives here, what we will be looking at, we'll be looking at some very basics of energy. We'll be looking at something called specific heat capacity, the energy involved in heating or cooling a substance, the energy involved with changes of state. Those first three objectives will pretty much make up what we talk about in this lecture. And then in the next lecture, we'll start looking at the law of thermodynamics, what we call enthalpy changes for chemical reactions, and so the actual energy involved in a reaction itself. The study of calorimetry, which is using some of those energetics to study some other things about chemical reactions. And then finally, we'll look at some various ways in which we are able to go about looking at some of those energy calculations. So let's take a look at just some of the basics of energy in general. For our purposes here, energy is the capacity to do work. And so if we think about any sort of energy, that's really what it is, right? It's the energy is giving the ability to do work in some way. The energy associated with a combustion engine provides energy to move the vehicle, and so forth. The energy involved with nutrition, the energy involved with food, gives our bodies the energy to perform all of their functions. Specifically, what we'll be looking at pretty heavily is the transfer of heat. That's the other aspect of energy. And we'll be looking much more so at that aspect in this class rather than the ability to do work. Two different types of energy. We have kinetic energy, which is the energy associated with motion. There's a formula for kinetic energy. If you've taken physics, you've probably worked with that formula quite a bit at this point. But kinetic energy equals 1/2 times the mass times the velocity squared. For our purposes, we will be talking about kinetic energy a fair bit when we begin to discuss gases and temperature in a lot of detail, because thermal energy, the motion of particles, has a lot to do with some of those properties, which we'll again be talking about in a few weeks. But also with kinetic energy, there's things like mechanical, the actual movement of things, electrical kinetic energy, the movement of electrons through a conductor, sound energy, and so forth. Again, those aren't really applicable for us in this class, but it's just important to know that those are various forms of kinetic energy as well. There's also potential energy. Potential energy is energy associated with either position or composition. Again, if you've taken physics, you're probably familiar more with, especially with gravitational potential energy, where something that's held maybe at a height here is going to have a different potential energy than something that's held at a height right here. And so something that's here will be able to gather more energy as it moves compared to something that's held here. And that's gravitational potential energy. The potential energy of me holding a baseball on the ground versus the potential of me holding a baseball at the top of a skyscraper. Much more potential energy at the top of that skyscraper. For our purposes, we are looking more at potential energy as it relates to composition. And so chemical potential. What sort of energy is stored within a chemical bond that might be able to be released, or the energy that's required to form a chemical bond. And so we'll be looking at some aspects of energy having to do with composition, chemical potential, quite a bit in here. The law of conservation of energy is going to be the backbone of a lot of the calculations that we do in this unit. Similar to the law of conservation of mass, remember the law of conservation of mass stated that matter cannot be created or destroyed. Law of conservation of energy says the same thing. But in terms of energy, energy cannot be created or destroyed. The total energy of the universe is completely constant. We can transfer energy. Energy can move in between systems, and that's, again, going to make up a large basis for what we talk about in this unit, that energy can be transferred around, but it cannot be either created or destroyed. And so the total amount of energy does remain constant. We can express that mathematically, where delta U, and so our change in energy is equal to 0. Delta U equals Q plus W. Q stands for heat and thermal energy, and we'll be using that abbreviation for energy a lot in this unit. So just keep that in mind. Whenever you see a lowercase q, we're talking about heat and thermal energy. So the total energy of any system equals that heat, that thermal energy, plus the work that's completed. Now, again, for our purposes here, we're not going to focus at all in on the work. We're going to assume for a lot of what we do, and your textbook talks about this. I'm not going to spend much time talking about it here, but any work that's done in any of our systems is what we would call pressure volume work, which is going to remain constant. And so for our purposes for this class, we assume that all of the energy that is all of the energy that's part of a system or part of a reaction is all in the heat. It's all in the thermal energy. And so that's what we are going to focus on. Those of you who are in engineering, you're going to focus in a lot on work in some of your various engineering courses. And you'll probably focus in on the combination of those in a fair bit of your engineering courses. For instance, when we think back to the example of the automobile and the energy that it takes to move an automobile, of all the energy in a combustion reaction, some of that is absolutely released as heat, some of that is released as work. And so both of those factors would have to be taken into account when you're looking at energy sort of on that scale. But again, in here, we're looking more at heat energy. And so we're going to be looking at the thermal energy or chemical potential energy of our various systems. When we're looking at thermal energy, so again, we're looking at kinetic energy that's associated with the random motion of particles. We talked about this a little bit when we looked at states of matter, and when we looked at gases, for instance. Gas particles are all just floating around, flying around, banging into each other, as opposed to particles in the liquid phase are more sort of stuck together, sliding around a little bit, but really sort of stuck where they are. And then the solid phase, they're really stuck where they are, just a little vibrating pretty much. And so we think of phases of matter in those terms with the particles having differing levels of kinetic energy. The kinetic energy of particles in the solid phase doing this is obviously a lot less than the kinetic energy of particles in the gas phase doing this, and all bouncing around and slamming into each other. We also have kinetic energy, chemical energy at this molecular level, which we will talk about, which is associated with the arrangement of particles. And so how are the particles in a compound actually hooked together? How are they arranged? What types of bonds exist between the atoms in these various compounds? And so that's a lot of stored energy. That's a lot of potential energy waiting to be released by whatever means we might be using. And so, like I said, we're going to be working a lot with heat for most of what we do in terms of energy. And so we're looking at the transfer of this thermal energy. And heat is always transferred from hotter to colder. Always, always, always. It's, for some of us big science nerds, it's a pet peeve for us sometimes to hear, like, if the freezer's open and somebody says, oh, you're going to let all the cold air out. It's not the way that thermal energy works. That's not the way that thermal energy is transferred. Thermal energy is always transferred from hotter to colder. And so even though it feels like the cold air is coming towards you when you open up the freezer, what's actually happening is that the warmer air from outside is going in. And so heat is always, always, always transferred from your hotter to your colder, from a higher kinetic energy state to a lower kinetic energy state. And the symbol that we use for heat, like I had mentioned, is Q. You're going to see that quite often. And so if you hear Q equals whatever, that's what we're talking about. So we're talking about that thermal energy. We're talking about the heat involved in whatever system that we're looking at. We talked about intensive and extensive properties when we talked about physical properties of matter quite a while ago now. We were talking about that in one of our first lectures back in September. And we had said that the extensive properties are properties that depend on the amount of material that's there. They depend on the amount of matter that's present. And so something like mass. Obviously, the more matter that we have, the higher the mass is going to be. And like volume, the more liquid that we have, the more volume we're going to have of that liquid. So those are extensive properties. They depend on how much we actually have. As opposed to intensive properties, which are properties that are completely independent of the amount of material. Density was an example that we used there. A small little thimbleful of pure water will have a density of pretty much 1 gram per milliliter. Every gram in that every milliliter in that thimbleful is going to weigh a gram. An entire tub full of pure water is going to have a density of 1 gram per milliliter. A milliliter of that tubful is going to weigh a gram. And so it doesn't matter how much of the substance that we have, the density is going to remain the same. And so we're going to use that to differentiate between heat and temperature. Heat and temperature are terms that are quite often sort of used interchangeably, and people confuse the two, but they are very different things. They're related to each other, but they are different. And so remember that heat is our transfer of energy from hotter to colder. Heat is an extensive property. The amount of heat, the amount of energy that is being transferred is going to depend on how much matter that we have. Whereas temperature is a measure of the intensity of that heat, not necessarily the amount, but the intensity of that heat. It makes it an intensive property. And so for an example, if we have a drop of boiling water versus a pot of boiling water, so remember that boiling point, one of our changes of phase, boiling point is intensive. It doesn't matter how much of the substance we have. Water is going to boil at 100 degrees Celsius no matter how much we have. It's an intensive property. And so that drop of boiling water is at 100 degrees C. That entire pot full of boiling water is at 100 degrees C. So they both have the same exact temperature. Doesn't matter how much of it there is. They have the same temperature, but the amount of heat is going to be very different. It takes a lot more heat to get that pot to boiling than it does for the drop of water. And so there's our difference, is that heat is an extensive property that will depend on how much we have. Temperature is an intensive property where it doesn't matter how much of the material that we actually have. Another way to think of it is think of that same pot of water, the same drop of boiling water versus the same pot of water. They're both starting out at room temperature. So they're both starting out at the same temperature. Again, doesn't matter how much of it we have. And then we want to raise them both to boiling point. It's going to take a lot more energy to get that pot up to 100 degrees C than it is that drop. And so it's because there's more mass of it there. So the heat involved, that energy involved with the more mass, means that it's extensive. It's going to take more energy for the thing with more mass to get to the same temperature. Let's talk units. What sort of units that we use with energy? The official SI unit of energy is the joule, and we use a capital J for that. It's a derived unit. Remember, derived units are just combinations of some base units. A joule will break down to a kilogram meter squared per second squared. We're not going to really worry too much about that. We're not going to use this for much for our purposes, but just sort of it's useful. It might be useful to know where that comes from. So that's the official SI unit. We will quite often use kilojoules, depending on what sort of system that we're talking about, because we're quite often, though, are talking about thousands and thousands of joules. So it's useful for us to use kilojoules sometimes. Another energy unit that we're going to run into a fair bit is calories. And so one thing to note when we do talk about calories, there's a difference here between the big C and the little c. The lowercase c is the actual energy unit that we might be using in chemistry. And 1 calorie with a lowercase c is equal to 4.184 joules. That's a conversion that we're going to use quite a bit, and that's going to be one that's very useful for you to know. And so just, you're going to want to know that. It's going to be a conversion that we'll use fairly often. A calorie with a capital C, that's your nutrition calorie right there. So when you're looking at the nutritional label of your Twinkie, whatever food you might be eating, it's always going to be, or officially anyway, it's a capital C. And so 1 food calorie equals 1,000 calories, or 1 kcal for what we use. And so that's another thing to always keep in mind, is that when we're talking food calories, it's a capital C, and that's different from the calories that we're going to use, that we might see as a unit in some of the various things that we encounter. And so joules or calories. What we have to do now, before we can really move on and really look at some of the details of energy, is we have to consider what we call the system and the surroundings. So when we look at energy, or the only way that we can really measure energy is by measuring the transfer of it. We'll talk about some ways, or a few ways in which we can calculate sort of the inherent heat that a substance holds. But one of the more common ways that we will measure heat in general is by looking at the transfer of heat, the transfer of energy. And so we have to look at the direction of that flow. Are things transferring into the system or out of the system, and so forth, which means we really have to define the system and the surroundings. The technical definition of the system is it's the part of the universe that we are studying. For our purposes, that's going to usually mean like the reaction or the contents of a beaker, something like that. But usually when we look at it, we're going to be, like I said, we're looking at maybe a particular reaction as being our system, or a particular sample of metal, something like that. It's whatever we're actually looking at. We can have an open system where the system is open to the surroundings, or a closed system where the system is not open, or even an isolated system where things are pretty much completely just, where the system is utterly isolated from the surroundings completely. The technical definition of surroundings, everything else. Everything else is the surroundings. And so for our purposes, what we are really going to be looking at when we talk about system and surroundings, or sorry, let me back up. And so let's just look at some sort of some visualizations of this. And so here we have surroundings. It's just sort of everything outside of our system. So again, our system is whatever we're actually studying. And so whether it be a chemical reaction, or whether it be a lump of metal, something like that. But we've got the system that we're studying, and then we have the surroundings, which are everything outside of that. If heat is gained, so if heat is gained by the system, so again, let's look at the flow of that energy. If heat is gained by the system, then that means that energy is moving from the surroundings into the system. And so heat is gained. So, and this is where it's important to really keep in mind this idea of system and surroundings, because we're always looking at energy from the perspective of the system when it comes to defining our direction of heat flow, our direction of energy flow. And so since we're looking at energy from the perspective of the system, if heat is gained, then our Q is going to be a positive number. It's going to be greater than 0. Because heat, again, is flowing into the system. And so our system is ending up at a higher energy level than where it was. And so heat is gained by our system. And so Q is going to be positive. As opposed to if heat is lost. If we are transferring energy from the system out to the surroundings, then Q is negative. Q will be less than 0. Because again, we're looking at it from the perspective of the system. We had energy here, our energy decreased, and so we lost energy. The system lost energy. So Q would be a negative number. We have, of course we do, definitions or vocabulary for each of these scenarios. In an endothermic change, that's where heat is flowing from the surroundings into the reaction. And so endothermic means that we are gaining energy. And so the system is gaining energy. The system is absorbing heat. And so heat is flowing from the surroundings into the reaction. As opposed to an exothermic system. In an exothermic system, our system is losing energy. Exothermic Q is negative, and so our system loses energy to the surroundings. Now let's take a look at why it is so important to keep in mind this direction of energy flow. Just make this smaller. Let's bring up our screen here. And so when we're looking at this direction of our energy flow, sorry, let me just pause for a second. Sorry about that. I wasn't sure that my screen was actually sharing for a second, but it looks like it is. So, okay, let's look at our direction of energy flow for just a second. And so let's say that we have a beaker. Our beaker is filled with some water. So we have some water in here. Let's say we have 2 beakers. Both filled with water. And in each of these beakers, we have something for a reaction. And I'm just going to picture the reaction as just this big red thing. And so when we define our system and our surroundings here, in each of these cases, our system is the reaction that we're looking at. Now, the technical definition of surroundings is everything else. But realistically, when we're looking at surroundings for our purposes, we're looking at where the reaction is taking place, the medium that the reaction is taking place in. And so here, we can see that our surroundings is going to be the water. And so let's think about each of these different types of energy changes, of energy flow. When we're looking at an endothermic system, so remember in an endothermic system, our system, our reaction in this case, is absorbing energy. It's gaining energy. And so in this endothermic system, so here, this one we're looking at the endothermic example. If I can spell endothermic. So there's our endothermic example. Our system is pulling in that energy. Our reaction is pulling in that energy. Think about the effect that that has on the surroundings. What's that going to do to the water? So our water is our surroundings. Our energy flow is moving into the system. That means our energy flow is moving out of the surroundings. Our energy is flowing from the surroundings into the system. And so the water, in this case, in this endothermic reaction taking place in a water in a beaker, is going to get cooler. And you would actually feel that. If you were holding this beaker, if the energy flow was enough, you would feel that happening. You would feel the water. You would feel the surroundings get colder. If we look at the opposite, see if my yellow marker will be, I think that'll stand out enough. We'll see. So let's look at the opposite scenario. Oh yeah, there we go. So now we have an exothermic energy flow. Our energy is moving from our system, it's moving from our reaction out into the water. And so our water, our surroundings are going to heat up. So the water is going to warm up. Now let's remember what we said about Q for each of these scenarios. In an endothermic scenario where our system is gaining energy, Q is positive. An exothermic system, our system is losing energy, Q is negative. And so here in our endothermic, Q is going to be positive. In our exothermic, Q is going to be negative. This is why it's so important to really take a second and think about the system and think about what's happening to the system. Because if we were to literally to be holding these in our endothermic example, our endothermic reaction, so we're running this one, we're holding our beaker, we're going to feel this get colder. But that's because we're feeling the effect on the surroundings. Our system is losing energy. So our Q is going to be positive because the system is losing energy to the surroundings. Sorry, other way around. Our surroundings are losing energy to the system. The system is gaining that energy. Our reaction is gaining that energy. Likewise, the opposite with our exothermic process. In our exothermic process, Q is negative. Our system, our reaction is losing energy. It's losing energy to our surroundings. So since our system loses energy, that's negative, but we would feel the effect in our hands as we're holding this. We would feel this as heat. We would feel this get warmer. But we're, again, remember that we're feeling the effect on the surroundings. And so always keep that in mind when because it's going to become very important for us throughout this whole energy section to really pay close attention to our signs. And in fact, in homework and on the exam, if you get the sign wrong of your energy change, you get the problem wrong. Because it's not only important to be able to calculate how much energy is being transferred in these processes that we talk about, it's also vital to be able to recognize the direction of that energy flow. And that's what the sign of Q is going to tell us. Is our energy moving from our system to our surroundings, in which case it's an exothermic system or an exothermic process, or is our energy moving from our surroundings into our system, where it's endothermic and Q would be positive. So always take that pause to just make sure that you're recognizing the direction of energy flow and that you're thinking about that flow from the perspective of the system, of the reaction or the piece of metal, whatever it may be, and assigning a sign appropriately to that process. So let's look at some ways that we are going to use this now. Some ways that we're going to look at and use some of these energies. Specific heat capacity is the first really sort of important, I guess, energy factor that we're going to run into. The specific heat capacity is the quantity of heat, the amount of heat that's required to raise the temperature of 1 gram of a substance by 1 Kelvin. So that's the official definition and the official temperature unit in science and in chemistry is Kelvin. We'll talk much more about Kelvin when we talk about gas laws and temperature in a few weeks. For now, just we're going to note that Kelvin, or to convert from Celsius to Kelvin, we add 273.15. And so since it's a straight addition, since we're just adding 273.15 to our degrees C to get to Kelvin, that means that a change in Kelvin, a change of 1 Kelvin is, for instance, is equal to a change in 1 degree C. And so I just point that out because the technical definition of specific heat capacity does use the temperature scale of Kelvin. We're going to use mostly degrees C because that's what we usually measure in. And so they can be thought of as being used interchangeably when it comes to something like this, because we're talking about temperature change, and temperature changes will be equivalent between Kelvin and degrees C. And so specific heat capacity in general we're going to think of it as just it's the amount of heat that we need to raise 1 gram of a substance by 1 degree. And so that's obviously going to depend on how much we actually have, right? The amount of heat needed is going to depend on how much of the substance that we have. It's going to depend on how much we're actually changing the temperature by. It's going to depend on the identity of the material. Some materials are easier to heat up than others. And we can gauge that by actually comparing the specific heat capacities of various things. Higher specific heat capacities mean that it is more difficult to change the temperature of that material. We would need more energy. And so if we have a gram of each of these substances, and we're trying to raise it by 1 degree C, it's going to take us 0.897 joules to do that to aluminum. But it's only going to take 0.129 joules to raise the temperature of gold by that same amount. So it's going to take less energy to raise the temperature of gold compared to what it would take to raise the temperature of aluminum. And we can see that water, very high specific heat capacity. And this is the reason, one of the reasons why water is so good at holding energy, because the opposite is true. So if we think about energy flowing in the other direction, we think about something losing energy, it's going to take more energy loss. We have to lose more energy. We have to lose more joules in order to reduce the temperature of water by 1 degree as compared to something like iron. And so water acts as a tremendous heat sink, or a tremendous energy sink, thermal energy sink. It holds heat much better than a lot of other substances. And so specific heat capacity in general is a physical property of substances. If we have a completely unknown substance, if we have an unknown metal, if we have a way to find the specific heat capacity of that unknown, we might be able to identify the metal, right? If we have 2 different unknowns, if we don't know if what we have is either aluminum or iron for whatever reason, then we can set up an experiment to measure the specific heat capacity. And if we measure this and we get a value of 0.92, again, keeping in mind that it's experimental data, real data, so it wouldn't necessarily be dead on, but if we get 0.92, that's pretty close to the specific heat of aluminum. And so we can say, yeah, it's probably aluminum and not iron. And so we can use this. And in fact, we're going to look at calculations doing that in just a few minutes. We're going to use this equation right here a lot throughout this unit. Q equals mc delta T. I'm not sure why I have it rearranged like this. Usually I hear it in terms of mc delta T. In fact, I'm going to pause the video real quick to just change that, because I definitely prefer mc delta T. So I'll be right back. There, that makes me feel better. Yeah, that's just, I have no idea why it was arranged like that in my slide. I've always just said mc delta T. So here it is, mc delta T. Q equals mc times delta T. Q, again, that's our measure of heat. That's our energy gained or lost as heat. M is the mass of our substance. C is our specific heat capacity. Delta T is our change in temperature. If you haven't encountered that yet, if you haven't encountered the delta symbol in science, that just means change. So delta T is our change in temperature. So our final temperature minus our initial. And it's also important to get that right. So delta T, the sign of delta T is going to matter for us, because that sign of delta T, if this is positive or negative, that's going to change our sign of Q. So we have to be mindful of that. These signs are going to matter. A positive Q would indicate an endothermic process, whereas a negative Q would indicate an exothermic process. So we have to be mindful of that when we are looking at our temperatures. So here's an example here. And so we have 50 grams of water. It's being warmed from 25.3 to 33.7 degrees C. And we want to know what amount of energy has actually been transferred in order to heat that water. And so, and we have the specific heat of water right here, 4.184. joules per gram degree C. If you haven't seen this symbology written like this, by the way, just remember that, so this was 4.184 joules gram degree C, both to -1. Just remember that a -1 as an exponent is the same as 1 over that variable. And so you might see units written like this sometimes in chemistry and in science. And so this 4.184 joules gram -1 degree C -1 just means 4.184, and then our units are joules. Gram to the -1 just puts gram down here, and degree C. So that's all that means. And so we have this example here. And so go ahead, pause the video now, and do this calculation. See if you can come up with the right amount of energy here. Now you're back. Hopefully you really did pause the video. If you didn't, do that. Pause the video and do this calculation. And hopefully when you do so we have our specific heat, our C, 4.184 joules per gram. And we're using Kelvin and degree C kind of interchangeably. Keep in mind they are different, but you may see them used interchangeably in equations like this. Well, then times our mass. It is very important that our mass, however, be in grams. That's key because our specific heat is using units of grams. So our mass has to be in grams here too. So times our mass of 50 grams times our temperature change of 8.4. Let's remember that 8.4 is our delta T. And so our delta T remember equals our final temperature minus our initial temperature. And so here we're saying that we're warming from 25.3 to 33.7. And so our final temperature is 33.7. Our initial temperature was 25.3. And so our temperature change was 8.4 degrees C, or 8.4 Kelvin. What I would do if I were you is I would get into the habit of, even with your delta T's, I would put a positive sign here just to make sure that you're keeping track of it. You definitely don't have to. I mean, it's not something that you would be marked wrong if you didn't put a positive sign there. But to me, it just helps make sure that you're keeping track of the temperature changes to make sure that we end up with a correct sign of Q. And so it's a positive 8.4. That's our temperature change. And so we plug that in, and we get plus 1757.3 joules. I know the sig figs are a little off there. Don't mind that. So I think it's also always helpful with these problems involving energy to just take that second to think about if your sign does make sense or not. And so let's think about that one here. We had a positive temperature change, and so we have a positive Q. Positive Q indicates an endothermic process that indicates that our energy has increased. And so let's think about if that makes sense. We are taking water and warming it up from 25.3 to 33.7. And so our system in this case is just water. Our system is being warmed up. And so if we just take a look at what we're doing, if we just think about what we're doing here. So again, we have just a beaker of water. And in this case, the water is our system. Sorry, there it is. So the water is our system, and that's being warmed up. So we can picture maybe a little fire down here. Here's my fire. Oh, that's a fire. There you go, throw some yellow in there. So there's our fire warming up the water. And so the fire in this case would be our surroundings. And so the heat is being transferred from our surroundings into the water. And so the water, being our system, is gaining that energy because the water has to gain energy to warm up. So it is an endothermic process, and so we would expect a positive Q value. And so it'll be really helpful for you to just to take those few seconds at the end of any sort of temperature, any sort of energy problem, thinking about if your sign makes sense. And so take that time to do that. So let's look at another example here. So now we want to know the amount of heat needed to warm 250 grams of water from about 22 degrees to up near close to the boiling point of 98. And we have the specific heat there. So again, go ahead and pause the video and use our heat equation, Q equals mc delta T. Plug it in and see if you can come up with the right answer. Hopefully you came up with something about like this, 7.9 times 10 to the 4th joules. Again, we have our specific heat, our 4.184, our grams, our 250 grams, times our temperature change, our delta T here will be equal to 76 degrees C. We take all those, we multiply them together, and we should get 7.9 times 10 to the 4th. So now here's a different example. So now we want to know the specific heat of silicone. Now we're looking for the specific heat. If it takes 192 joules to raise the temperature of 45 grams by 6 degrees C. And so let's just take a look at that. And so we're still going to use our baseline equation. We're still going to use Q equals mc delta T. That's our heat equation. We're going to use this heat equation for a lot in this unit. But now we want to calculate for the specific heat. So let's just algebra this. Algebra is indeed a verb. We're going to algebra our equation. We need to solve for C. We need to solve for our specific heat. And so when we perform the algebra on that, in order to solve for C, we see that we need to just divide both sides by M and divide both sides by delta T. And so we end up with C, we end up with our specific heat equals Q over mass times delta T. And that's what we have here. We have our Q over our mass, our 192 joules, divided by the mass times 6 degrees C. The formatting ended up a little bit weird here, and while I have you right here, or I have it right here, I'm just going to pause the video and fix this. Be right back. And bummer, I found that I wasn't actually able to change that because it's an image, not an actual, not text. So anyway, that's my problem, not yours. But so we can the moral of the story here, though, is that using our heat equation, using our Q equals mc delta T equation here, we can solve for any one of those 4 variables, as long as we know the other 3. If we're given the heat and we're given the specific heat and we're given our delta T, we can find the mass, and so forth. If we know our heat, our mass, and our specific heat, we can find the temperature change, and so on and so forth. As long as we know the other 3, we can find the 4th item. And so this is the way that we might be able to go about, and we're going to see some more specific examples of this, but this starts to show you the way that we might be able to identify the metal if we have an unknown metal. Let's say we didn't know this was silicone, but we were able to measure this amount of heat that it took to raise the temperature, and we were able to find the specific heat, then we might be able to identify it as what it is. And so, and we're going to look at that, in fact, right now. And so, like density, specific heat is an intensive property. So the specific heat isn't going to change no matter how much of the substance we actually have. And so we can measure it experimentally. And so let's think about this scenario here. Let's think about if we have a hot piece of metal. We have a hot piece of iron. It's up at about 99.8 degrees C. So we've heated this up. We've heated up this 55 grams of iron. So we're taking this big chunk of iron here that we've heated up. And we're going to go ahead and drop that down into water. The water is at 21.0 degrees. And we know how much water we have. We know we have 225 grams of our water. And so we're going to take this hot metal and we're going to drop it down into the water. Now, without even thinking about the numbers for a second, let's just think about what's going to happen with our heat. Think about what's going to happen with our energy. So we're taking this hot chunk of metal, we're dropping it down into water. Let's think about this from the perspective of the metal for just a second. So this metal at 99.8 being dropped down into water at 21, what's going to happen with the heat? What's going to happen with the energy of this metal? It's going to lose energy, right? It's going to lose its energy to the water. Likewise, the water at this 21 degrees is going to gain energy. And so the energy that the metal loses will be gained by the water. And so the metal is going to cool down. The metal is losing its energy. So the delta T of the metal is going to be negative. The metal's going to decrease in temperature. Our final temperature, when we drop this in and we allow the temperatures to come to an equilibrium, our final temperature there is 23.1. And so our metal went from 99.8 to 23.1. So our delta T of our metal is negative. That means our Q of the metal is also going to be negative. Again, which just makes sense because we know that the metal had to have lost energy. And so the metal went through an exothermic process in which it lost energy. And so Q would be negative. The water, however, warms up. And so the delta T of the water is going from 21 to 23.1. Delta T of the water is positive, means that our Q of the water is positive, which again just makes sense because we know that the water had to have gained energy. That's an endothermic process. Endothermic processes have a Q that's positive. And so let's think about those numbers for just a second. The law of conservation of energy tells us that the total amount of energy involved in this process has to be conserved. No energy is created or destroyed. And so this is an isolated system, and all of the different energies involved, if we add them all up, have to be equal to 0. And so what we have going on here is, again, our metal. So this is just another example, but very similar. Metal heated to 100 degrees C. So we put some metal into some boiling water, maybe. It's heated up to 100 degrees C. We drop that into another sample of water. And so the heat lost by the metal, we can set up an equation for that, right? So just like this is an example here, our metal is losing heat, and we can set up an equation to see how much of the heat was actually lost. That's going to be equal to the amount of heat gained by the water. That's what the law of conservation of energy is telling us. Is that when we look at these two different processes here, we look at our energy lost by the metal as it cools down, and our energy gained by the water as it heats up, those two energies have to be equal. Let's just sort of use my keen art skills to look at that. Again, here we have our beaker full of water, and we're going to go ahead and just drop a piece of metal down into this. And so this metal is going to lose energy out to the water. And so as the metal cools down, it's losing this energy out to the water. And so the metal, again, is losing energy. So we have a Q of the metal. The water, so here's all of our water in here. The water is gaining that energy. And so the Q of the metal, since the metal is losing its energy, it's cooling down in an exothermic process. And so the Q of the metal is going to be negative. The Q of the water is gaining the energy that the metal loses. The Q of the water is positive. Law of conservation of matter tells us that those two energies combined have to be equal to 0. And so our negative Q of the metal plus our positive Q of the water taken together must be equal to 0. Another way to look at that is that our Q that the water loses must be equal to, or sorry, the Q that the water gains must be equal to the Q that the metal loses. There's our conservation of energy. The heat lost by the metal equals the heat gained by the water. We can use that. We can use that information. And so thermal equilibrium just means that energy is going to transfer as heat from an object at a higher temperature to an object at a lower temperature. And that will continue until both objects are the exact same temperature. And so let's look at an example using this idea of thermal equilibrium and this idea of the law of conservation of energy. So here we have a 145-gram sample of copper. It's at 100 degrees C. We place it into 250 grams of water at 25 degrees C in a calorimeter. Calorimeter is just a device that enables us to measure some temperature changes. And it's something that is fairly insulated. Quite often in general chemistry labs, for instance, a calorimeter is nothing more than 2 styrofoam coffee cups nested together. Holds energy very well, is insulated very well. And so here we've got this system going on. And when the system reaches thermal equilibrium, now the temperature of the water is 28.8 degrees C. So again, remember what thermal equilibrium means. This means that the water is now at 28.8 degrees C. It also means that the metal is at 28.8 degrees C. From this, we want to calculate the specific heat of copper. And so let's take a look at what that calculation is actually going to look like. All right, so let's walk through this calculation here. And so what we're going to do, again, if we just sort of keep in mind what is going on here, we have our calorimeter, we have our sample of water. So there's our water in here. Our water is starting, and so our temperature initially of our water equals 25.0 degrees C. We have a sample of our metal, and our temperature initially of our metal equals 100 degrees C. And so then we're going to put them together. So we're going to drop our metal into our water. And we have a final temperature of that system of 28.8 degrees C. And so keeping in mind that that has to be the final temperature of both the metal and the water because we've reached a thermal equilibrium. And so if we keep in mind our direction of energy flow, and so energy had to have been lost by the metal, and so we have a Q lost by our metal. And so since that is an energy loss, it's an exothermic process, we're going to have our negative sign there. And that is going to be equal and opposite in sign to the energy gained by the water. All right, law of conservation of energy tells us that the energy lost by the metal has to be equal and opposite to the energy gained by the water. And so we have our Q expressions for both of those. Now, we're just going to use our calculation for Q. Just zoom back a little bit. There it is. Q equals MC delta T. And so we can set MC delta T expressions. Showed you the answer a couple times. We can set MC delta T expressions for both the metal and the water. So Q equals MC delta T for the Q lost by the metal. So we have our mass of the metal times our C of the metal times our delta T of the metal. And we said this is going to be a negative. That's going to be equal to our mass of the water times our specific heat of the water times our delta T of the water. And we have values for most of these. We know the mass of our metal, shrink that a little bit so we can see the negative sign. We have the mass of our metal at 145 grams. The C of the metal, the C of the copper, that's what we're looking for. We know we can find our delta T of the metal, our final temperature. It's 28.8 degrees C. Our initial temperature of the copper was 100 degrees C. That's going to be equal to our mass of the water at 250 grams, or 250.0, times our specific heat of the water, which we are given, 4.184 joules per gram degree C, times our delta T of the water, 28.8 minus 25.0. Both degrees C, I just left those off because I was running out of room. Now we can simply set this up to solve for the C of the metal, right? We algebra this. In order to solve for C of the metal, I'm just going to divide both sides by my 145 grams and my 28.8 minus 100. So I'm just dividing both sides by these two terms right here. So I end up with C of my metal equal to 250.0 grams times 4.184 joules per gram degree C, 28.8 minus 25.0 degrees C, all divided by 145 grams, and my temperature change of my metal. I do all this out. I plug all this into my calculator. Sure enough, I get an answer of 0.385 joules per gram degree C. And so all I'm doing here is I'm taking advantage of the law of conservation of energy, which says that my heat lost by the metal has to be equal to my heat gained by the water. And I use that information to set up Q expressions for both, and I solve for whatever it is that I'm looking for. Now, I put in all the numbers here and worked with it that way. Honestly, the way that I use, and because I just wanted you to see the full Q expressions on both sides and how the numbers worked in. Honestly, I usually do my manipulation, my algebraic manipulations, before I ever put any numbers in. So I would probably have, so we have our negative heat lost by the metal. And sorry, I didn't really pay as much attention to the negatives there as I should have. But that's going to equal our positive heat gained by the water. And so we have our mass of the metal, our C of the metal, our delta T of the metal equals our mass of water, C of water, delta T of water. Sorry, running out of space. And so I usually actually manipulate my equation right here before I put my numbers in. So I would get my C of the metal equals my mass of the water times C of water times delta T of water, and again, all over the mass of the metal times the delta T of the metal, and then I would put my numbers in. Doesn't matter which way you do it, you're going to come up with the same answer either way. I've just always preferred to do all of my algebraic manipulation before I ever put any numbers in. Either way you wanted to do it, perfectly acceptable. And so here we want to see the amount of heat required to raise the temperature for a 100-gram piece of copper. So same idea, only now we don't have a thermal equilibrium situation. We just have a straight up Q equals mc delta T, because we want to know the amount of heat required, our amount of Q, in order to raise the temperature of 100.0 grams. We just calculated our C, 0.385, and we want to raise the temperature. Sorry, just 1 second. Sorry, just realized we were missing a key piece of information there. We want to know the amount of heat required to raise that 100 grams by 1 degree Celsius. So there's our delta T. And so we plug this in, and we come up with an answer of, oh, no, sorry. I just realized that it was okay the way that I had it written. 38.5. I'm going to change that anyway. Let's just hold on just 1 second. Okay, sorry about that. Sometimes I just realize midway through that, or I lose track of where I'm going. But so we wanted to just calculate the amount of heat required to raise this 100-gram piece of copper by 1 degree C. So we just plug that into our equation, our Q equals mc delta T, and we see that it'll take 38.5 joules of energy in order to accomplish that. So here's another example. We have a 57.4 gram piece of an unknown metal. We heat it up to 99.8 degrees C and then plunge it into a beaker of water. This beaker holds 225 grams of water. The temperature is 21 degrees C before we drop the metal in there. And it reaches thermal equilibrium at 23.1 degrees Celsius. And we want to know the specific heat capacity of this metal. So again, it's our same exact process. We are going to take our negative heat lost by our metal is equal and opposite in sign to the positive heat gained by the water. And so we can set up our different Q expressions. And so the heat lost by the metal, we have a negative mass of the metal times C of the metal times delta T of the metal, and equal and opposite in sign to our M of the water, C of the water, and our delta T of the water. Sorry, I keep losing my negative signs there. There we go. And so now we can just plug all this information in. Again, first, I like to just rearrange my equations. And so we're looking here for the specific heat capacity of the metal. So let's solve for our specific heat of the metal. So that will equal our mass of the water times our C of the water times our delta T of the water, all divided by our negative mass of the metal times our delta T of the metal. And so now we plug our numbers in. We have a mass of the water, 225 grams. We're given the C of water of 4.184 joules per gram degree C. And that's a number that you'll probably just memorize by the time we're done. We're going to use it so often. Times our delta T of the water. The water ends, our final temperature of the water, 23.1 degrees C. It started at 21 degrees C. That's all going to be divided by, we get a negative M of the metal, and our mass of the metal is 57.4 grams, times our delta T of the metal ends at 23.1 degrees C, started at 99.8 degrees C. And we plug this all into the calculator, and it's possible before I get through this calculation that my cat will come up and join me. We will see. Well, so we plug all this into our calculator, 225 times 4.184 times 23.1 minus 21, making sure to put that in parentheses here. If you're doing this all at the same time, but then divided by 57.4 times 23.1 minus 99.8, two sets of parentheses with my negative, and I get a value of 0.449 joules per gram degree C. And there's my final answer. And so we now know what the specific heat of this metal was. We were able to perform this calorimetric analysis. And so we found that it was 0.449. And so let's use this chart of specific heats to try to figure out what our metal was. There it is. Our unknown metal had to have been iron. So we can use this to identify what our unknown was. All right, this lecture actually took a little bit longer than I expected, so I'm going to hold off and I'm going to start in on energy and changes of state with our next lecture. And so we'll pick up from here next time. And so this concludes our introduction to thermochemistry, the chemistry of chemical processes and chemical reactions. And so we'll pick up next time looking at the energy involved with changes of state. Thanks for watching.